Okay, so let's work a couple of problems on the use of arrays in Python using NumPy. We already have NumPy imported np.array, but we'll do that again anyway. So problem 1 here is to make an array. Let's see, make an array called x from 0 to 5 with 1,000 points, and then create the following arrays from that. Plot each array versus x on a single plot. So first import numpy as np, and then x equals np. So we're going from 0 to 5 with 1,000 points. That'll mean using linspace 0 to 5 with 1,000 points. Then to create the other arrays, we can call this y1 is 2 times x, y2 equals x squared minus 3 times x plus 4, y3 equals np.sine 5 times x. So here we're using the array arithmetic. A scalar times an array is an array. An array squared squares each element 3 times an array. So, and then adding 4 to an array adds 4 to each element. And then if we operate on an array, we get the sign of 5 times each element of the array. Okay, and then we can plot it, plt, and let's import the plotting library here, plotlib.pyplot as plt, %matplotlib inline, and then at the bottom plt.plot xy1, and there we go. Single plot with all of the lines. If we add a semicolon at the end, we don't get the little plot marker. So there's an example, creating an array, creating some new arrays based on the first, and then plotting the results. Okay, let's go on to problem number 2. Problem 2, we have the ideal gas law. We're given m, r, and p, and we want to find the density for a range of temperatures. So we'll store rho and t as arrays and plot the results. So we do m is 29 kilograms per kmol. R can be 8314 joule per kmol K. P is 101,325 pascals. And then we'll make an array of temperatures. T equals np dot. In this case, we don't know how many points. I mean, we can guess, but we know the increment, so we'll do np.arange 300 to 1100 with increments of an increment size of 100. And if we print t, we can see 300 to 1,000 is given, so that's good. Then we'll store rho. So rho tab equals m times p over r over t, and then plot plt.plot t comma rho, and we get the result. Okay, so that's problem number 2. Again, we are making use of the fact that a is an array and the array arithmetic storing the result as an array. So this would work whether t was an array or if t were a single value, we would get the same thing. Of course, now rho is only a single point, but the actual calculation works whether t is an array or just a single value. Okay, let's look at problem number 3. We can redo that by writing a function for rho of t, and we'll call the function with an array of t and store the result. So let's go back and grab our code. And then we will def rho of t, and we'll put all this in here and just return this statement, rho of t, and we get that result. So in this case, we're passing in t as an array, and let's put this here. T is an array, And then we pass the array into our function row of t. So t is an array inside the function. And again, the array syntax works. So this quantity will be an array. We return this quantity and store it in this case, we're not storing it in a variable. We could if we wanted like my row, and then we could plot equals row of t, and then plot my row, and we get the same thing. So this is an example of passing in an array and returning an array and making use of the array arithmetic. Okay, let's look at problem number 4. Here we have an array of times t, and we want the array of differences dt between times. So we'll have a dt here and here and here. Between each of the blue lines we have a delta t, and we're going to store those differences in an array. So first, let's see. So here we've got an array already set up with the times, and it looks like we have the code here, so let's just go ahead and analyze that. So there's a couple of ways to do this problem. The first is the size of t can be found with len t, and we know that dt will be 1 less than that, because if we have 1, 2, 3, 4, 5, 6, 7, 8 lines, then we have 1, 2, 3, 4, 5, 6, 7 gaps, and the dt are the gaps. So we initialize dt to be an empty, np.empty, and the size is 1 less than t, so len t minus 1. And then we loop through each point and calculate the value. So we want to loop through each dt. So that one, that one, that one, that one, etc. So for I in range the length of dt, so I will start at 0, and for I is 0, the first gap, the difference is t1 minus t0. And so for a generic I will be I plus 1 minus I. And so that's the formula. dti is ti plus 1 minus ti. A simpler way to do this is with array slices, and that would be dt equals t1 colon minus t colon minus 1. And so t1 colon, so if we have elements 0, 1, 2, 3, 4, 5, then 1 colon would be 1, 2, 3, 4, 5, and colon minus 1 would be elements, so this is t, and this is t 1 colon, and if we do t colon minus 1, let's just space these so they're even, then this one would be element 0, 1, 2, 3, 4. And so when we subtract this array from this array, we're doing it element-wise. So we get 0.1 minus 0, 0.2 minus 1, 0.3 minus 2, 0.4 minus 3, 0.5 minus 4. And the result of that is stored in the sequential values of dt. So you'll have 0, 1, 2, 3, 4. So you can see that dti is equal to ti plus 1 minus ti, which was the same formula that we had here. So that's visually an indication for how this array slice version works. Of course, the 1 colon means start at index 1, 0, 1, and go all the way to the end. So if you don't put a number after the colon, it means the last one, all of them. And if you don't put an initial one, it starts at the very beginning. Okay, so there's that example. And then we can look at it, dt, and we get the same result. If we comment this, we can see we get the same result for the for loop as we get for the slice. Okay, so let's look at the next problem, problem number 5. We'll do this with a little more practical example, or a little more complicated example. So here we have an array of x points, 0 to 0.1 to 50. We're going to create this array. Then we're going to create an array y equals sine x. And then we're going to take numerical derivatives And for interior points, we'll use a central difference. And at the edge, we'll use a one-sided difference. And then we'll plot the results. So here we can go x equals np dot, we know the spacing again, so a range makes sense. We'll go from 0 to 50.1 by step sizes of 0.1. And then y equals np dot sine of x. And now we want the derivative, so we'll make some space for it. dy dx equals np dot, I don't know, empty or zeros. Let's do zeros for fun. And this will be the same size as y, because we want to do, let's make a little graphic here. Y is, we have point. So these ones are the interior points, and these ones are the end points. And if we have 1, 2, 3, 4, 5, 6, 7, 8 points, then we'll have 8 derivatives. So here we'll do the length of y. That's dy dx. Then let's do the first point. So dy dx 0 is this formula. That's the easiest one. Dy dx 0 can be written as y1 minus y0 divided by dx. And let's make that a big delta. And we need the delta, so delta x is x1 minus x0, and it's uniformly spaced, so they're all the same. All the dx's are the same. Now let's do the last one. We have this formula. So here we have, we're referencing this by the last point being n minus 1, so let's compute that so that it's available. N equals ln of dy dx, and then we can write, then we can write, if I can get my screen to work well, looks like we're out of space. Here, we'll just cheat a little bit, there. Okay, this can be n minus 1. And this can be n minus 1 minus n minus 2. So that's the last point. And then for the interior points, all these middle points, it's convenient to write an index variable I equals np dot a range. And here we'll go from point 1 to point, so if this is point 0, then that's 1, 2, 3, 4, 5, 6, 7, and this is also point n minus 1, and that's n minus 2. Okay, so for convenience we have some indexing there, and then we can go np dot a range. We'll go from 1 for the interior points up to n minus 1. And that will stop at 6. Great. Then we can go dy dx I equals, and then just type this formula. Y, sorry, need more room. Y I plus 1 minus y I minus 1 divided by 2 divided by d delta x. Great. Okay, perfect. And then we can plot this thing. So we know the answer is cosine x, so let's go ahead and plot it. plt.plot, and we'll plot x and dy dx, and also x and np.cosine of x, and see how they compare. And we have an error. Let's not plot it and run it. Whoops. Oh, yeah, that's not code. Okay, there we go. And let's see if we can see the plot. maybe. See the plot. Go. Go. Okay, we'll delete the code to see the plot. There it is. And they're basically the same thing. So let's put fewer points in there. Instead of 0.1, we'll do like 1 with 50 points. And then you can see that because it's more coarse, it's not a perfect agreement. So when we do 0.1 with 10 times as many points, we get a pretty nice looking plot there. Great. Okay, so this illustrates an index array I, and then notice how these formulas that we were able to write mimic almost exactly the index notation that we used for the equations, and we treated a different equation for the ends as we did for the interior points. Okay, this could be done with an array slice too, this last one, if we felt like it. But I think it's a little cleaner and a little easier to read if we set up an index array and then index directly in terms of I so that it's easier to read. Of course, you could do all this in a loop. If you did this over a for loop, you could, if your I was 0 or if I was the last one, otherwise we do this equation here. In general, using index arrays and array slices will be faster than for loops. Okay, let's look at problem number 6. Solve the rate equation below. T is 5 seconds using the explicit Euler method. There's the explicit Euler method. There's our rate equation. We're given a time step size, store the arrays, and then plot the answer on the same plot. Okay, so let's see. So we want an array of times. So T equals np dot, let's see, how long do we go for? Doesn't, oh, the T is 5, np dot linspace, well, we'll go a range again, 0 to 5.5 with a time step size of 0.5, and maybe we'll go delta T is 0.5, and then change this to be 5 plus delta T, and we'll put delta T in here so that we can easily change the time step size if we want to. And then y equals np dot, well, we could copy it just to initialize y, so t dot copy, and that initializes y. Then the initial point for y, y0 is equal to 1. And then for I in range, we'll go 1 to when y, do all the rest of the points. Then we can use this formula. Y, well, depends on how we want to do it. The way that I've written it here is with I plus 1. Let's go ahead and leave it the way it is, like that. Yi equals yi minus 1 plus delta t times this function, and the function here is that. So we'll have minus k times y minus 1. Okay, and we'll let k equal 2. Okay, alright, so fine, that works. And then we can see if it works. Okay, it seems to have worked. And we can plot the result, plt.plot, t comma y, and we get, again, see if we can slim this up a little so it's easier to read. Good, except that it doesn't look like we have very many points. So let's see, comment that, t, okay, yeah, so there aren't particularly very many points in this thing. Okay, let's change this, 05, okay, there we go, and then we can compare it to the exact solution, t comma y0 times np.exp of minus k times t, and we get those two. So we can now see the comparison, and the lines are pretty close, so our numerical method seems to be good. If we increase the step size, maybe make this 1, then you see a little difference. 2, see some difference. 3, 4, etc. Okay, so there's an example of solving a rate equation using the explicit Euler method with these with arrays. Okay, let's see. Do we have one more? Looks like we've got one more function, one more problem. Hayland equation relates the friction factor in a turbulent pipe to the Reynolds number, RE. So we're going to write a function to compute this thing, and then we're going to plot it. Epsilon over D is given, so let's see here. Okay, so we'll create a function, def f of RE, and we'll call it epsd, and then we code and return this thing. So we have return minus 1.8 times np.log 10 of epsd over 3.7 to the 1.11 plus 6.9 over the Reynolds number. And we need to do we need to solve for f, so it's all of that 1 divided by all of that squared. So I wrote that out of order so that I didn't have to keep track of as many parentheses. Okay, so there's our function. Now let's create an array of Reynolds numbers. RE equals, so uniformly spaced on a log scale. Create an array of 100 points uniformly spaced on a log scale. So we'll use log space for that, np.log space. And that is 3, 8, and 100 points. So with log space, that's 10 to the 3, and that's 10 to the 8th. So the numbers you give are 3 and 8, meaning it'll be 10 to the 3 and 10 to the 8th. It's a little different than lin space. Okay, and then call the function. So we can call this f Hayland equals f. Actually, let's call this f Hayland, and then we'll call this just f Hayland RE, and epsd was 0.001, and then plot it, plt.plot f comma, sorry, RE comma f, and it should be on a log scale, so we'll do plt.x scale can be log, and then we plot the result, and there's the friction factor as a function of Reynolds number. Great. So if we wanted to, we could do, instead of plot, we could do semi-log x, and then we wouldn't need the plt.x scale, and that works fine too. And we can add axes labels and whatnot. So the key thing here, though, is that, again, we're passing in an array of Reynolds numbers, and this statement works fine on the array because RE is an array, so this will be an array. And then we add that to a scalar, single number, and so it adds to each element of the array, and that's an array. And then we take log 10 of that, and then we times it by minus 1.8, and then we 1 over it and square it. And so it works fine whether RE is a single value or whether RE is lots of values. So if we do RE equals 2,000, then it also works fine. Of course, you're not seeing the plot because it's only one little pixel. Okay, so there's another example. And that's several worked problems with arrays.